Hello everyone and welcome back. What we're going to do in this session is very briefly run through a couple examples before I leave you with examples to complete on your own. A lot of this work, and this is a real theme that you'll see throughout it, it's not necessarily listening to my explanations as much as it is trying and succeeding or trying and failing. And the reason failing is useful is because it shows us where we've made mistakes. It explains to us exactly where the problems have happened, and that allows us to go back in the future and correct those mistakes. So again, just to rehash, we're continuing on with graphing today. I'm going to take you through two problems, and then as I explain, hopefully you're following along. If in any way you do have a problem, A, you can contact me as always, but B, you can rewatch the videos once you've attempted the problems. One thing I'm doing is I'm including the problems in the videos now. Before, I was sending these problems to you through Kakao, but now I'm including them in the videos. The reason for that is very simple. I want you to watch these videos. Even if this is relatively easy for you, and at this point, what we've done should be relatively easy for you because we've done a lot of it. But even if it is relatively easy for you, I'd still like you to watch the videos because this class is all about adaptation. It's about taking what we've learned and adapting it to new and different situations. We aren't necessarily in a scenario where we're able to teach you everything that you might encounter. Instead, I can get you a lot of the information, but it's then up to you to go in and apply that information to the unique problems we face both here in the classroom and also in any real life applications you may encounter that require linear programming practices to be employed. So without further ado, let's move on. Both of these problems are relatively simple. From this point, you will be asked to solve the problem, formulate the problem before solving it graphically. Now, I don't need you to follow all of the steps we've followed so far. It won't hurt you to follow each and every step, but it's not always necessary either. Instead, I leave it up to you to essentially formulate problems how you would like. But one thing I will caution is that on any exam or assignment, the problems will have to be submitted in a formal manner. They will have to be submitted in the same or using the same universal format that we've done for each and every problem. Min z, max z, your objective function, subject to, and then a list of your constraints. That is one place you do not have freedom. For these assignments, because you're not turning anything in, you can complete them however you would like. However, if it is a formal assignment, you will be expected to turn it in with your problems formatted in that universal format. So let's begin. This is example problem number 2 for graphing, and it's a pizza problem. You own a pizza restaurant, and you have just received an order for 100 pizzas for tomorrow. However, tomorrow is a holiday, so you are currently out of supplies. You also don't plan to open after preparing the big order, but you do need enough supplies to make the big order. To make 100 pizzas, you require 15 kilograms of pepperoni and 20 kilograms of cheese. You also have 2 ways of acquiring supplies. You can buy a large ingredient bag that contains 3 kilograms of pepperoni and 1 kilogram of cheese, or a small ingredient bag that contains 1 kilogram of pepperoni and 2 kilograms of cheese. The large bag is $5 and the small bag is $4. How do you meet your requirements and minimize your costs? So, we have here a very prototypical example of a linear programming problem. We have a goal to meet. We want to minimize our costs in meeting that goal. We also have several requirements that must be met in order to meet that goal. So let's have a look at all of this. Step 1, we're looking to find our objective function. And in this situation, we know that our objective function, we're trying to minimize z, and we have two choices, a large and a small bag. I'm not going to write all of this down, but as you just saw, I do have the collected information, but I will, for simplicity's sake, guide you through the process. So our large bag is $5, our small bag is $4. So our objective function is min z equal 5x1 plus 4x2. x1 represents the number of large bags, x2 represents the number of small bags. Now, we also know that we require 15 kilograms of pepperoni. If we require something, it becomes a constraint. So constraint number 1 is greater than or equal to 15 kilograms of pepperoni. A large ingredient bag, x1 is 3 kilograms of pepperoni. Small ingredient bag, x2 is 1 kilogram of pepperoni. So our first constraint is 3x1 plus 1x2 is greater than or equal to 15. Our second constraint, we require 20 kilograms of cheese. We know in a large bag there's 1 kilogram of cheese, in a small bag there's 2 kilograms of cheese. So our constraint becomes 1x1 plus 2x2 greater than or equal to 20. So in this situation, we have two constraints. Two decision variables, large and small bags, two constraints, requirements for pepperoni, requirements for cheese. We can see our constraints, our total question formulation here. Min z equals 5x1 plus 4x2, subject to 3x1 plus x2 greater than or equal to 15, and x1 plus 2x2 greater than or equal to 20. Now, from this situation, and going back to what we talked about last time, essentially, we have two scenarios. Two constraints that have to be graphed onto our graph. Two lines that guide us to where all resources are used at the maximum amount. C1 and C2. So, let's look here. We see this is just a summary of the information presented before, but it makes it a little more clear if anybody was unsure. None of this is critical information. But if we look at C1, 3x1 plus x2 is greater than or equal to 15. We have to graph this line onto our graph. And to do that, we need 2 points. We need an x1 point and an x2 point. To find x1, we make x2 equal to 0. So this is eliminated. 3x1 is equal to 15. 15 divided by 3 is x1. x1 is equal to 5. So x1 is 5, x2 is 0 is our first point on our line. We do the same thing. We make x1 0. x2 then becomes 15. So our second point is 0x1, 15x2. We see that here. So when x1 is equal to 0, right here, x2 is equal to 15. And when x2 is equal to 0, x1 is equal to 5. These are our 2 points on the line. This line represents everywhere where we are using 15 kilograms of pepperoni. If we buy 5 large bags, we have 15 kilograms of pepperoni. If we buy 15 small bags and no large bags, we have 15 kilograms of pepperoni. If we buy 10 and approximately 2, we will still have 15 kilograms of pepperoni. Every point on this line provides us with 15 kilograms of pepperoni. We have to repeat that process one more time for our second line. To find x1, we make x2 equal to 0, and x1 is equal to 20. So 20, 0 is our first point. And we do the same. We make x1 equal to 0, 2x2 is equal to 20. 20 divided by 2 is x2. X2 is equal to 10. So 0x1, 10x2. And we see that here. This line is the same. We did exactly for the first line what we did for the second line. Once we've graphed both of these lines, we have all of this relevant information now. Here, above these lines, because it's a minimization now. Before, when it was a maximization, it was below these lines. Now, it's above. Above this line, we have enough cheese. Above this line, we have enough pepperoni. Below this line, below both lines, we have not enough cheese nor enough pepperoni. Because it's a minimization, this changes. In this space here, it's above cheese, but below pepperoni. So we have enough cheese, but not enough pepperoni. So these are not possible choices. Here, we have not enough pepperoni. We have enough pepperoni, but not enough cheese. So these are not possible choices. In all of these areas up here, we have both enough cheese and enough pepperoni right here. But we're trying to minimize our costs. So we want to be above these lines, but actually right on these lines because we're attempting to minimize our costs. So right here, and right here are our 3 possible optimal solutions. Those represent the 3 points where we would be minimizing our cost, but also meeting our requirements. We don't know yet which one is cheapest. That one we'll have to solve algebraically. That is an example of a graphing problem from the problem formulation here. Once the problem is formulated, we plot line 1, we plot line 2, and we indicate these areas. If you have questions about this, as always, please contact me, and I will be able to help you hopefully. Okay, moving on. Very quickly, we've highlighted these 3 key points. These are the purchasing choices that would give us enough cheese and pepperoni, but only these 3 red circles represent where costs are minimized. So it is our optimal choice is one of these 3 circles. Our second problem is a phone case and phone charger problem. This is, again, a very simple problem, but for now is useful because it allows us to see, once we have a problem that's not very difficult to formulate, how to effectively graph those problems. You own a manufacturing company that needs to choose how many phone cases and how many chargers to manufacture. You know that you have both 64 hours of labor available and 48 kilograms of supplies available. You also know that each case requires 8 hours of labor and 2 kilograms of parts to produce. You also know that you require 4 hours of labor and 12 kilograms of parts to produce a charger. You make $12 per case sold and $32 per charger sold. However, you don't know how many to produce to maximize revenue, so you must determine that with linear programming. So, again, before we can begin graphing, we have to formulate the problem. We know that we are trying to maximize revenue, as stated right here, maximize revenue. So, we need our two decision variables, phone cases, and chargers. Phone case, phone charger. And we're trying to maximize revenue. So in this situation, we see here that it is $12 per case sold, so 12x1, and $32 per charger sold, 32x2. So our objective function is maximize z equals 12x1 plus 32x2. Then we go into our constraints. We have 64 hours of labor available. Each case requires 8 hours of labor. Each charger is 4 hours of labor. So 8x1 plus 4x2 less than or equal to 64. We have 48 kilograms of supplies. A charger is 2 kilograms of supplies. A phone case is 2 kilograms of supplies. A charger is 12 kilograms of supplies. So 2x1 plus 12x2 is less than or equal to 48 for our second constraint. So now we have our problem formulated. We see that here. 12x1 plus 32x2 is our objective function. And we have two constraints. 8x1 plus 4x2 is less than or equal to 64. That's our labor available. 2x1 plus 12x2 is less than or equal to 48. That is our supplies available. Once we have this information collected, we can begin graphing. Now, the first thing we do is draw the graph, and then we draw our constraint lines. For line number 1, we want our first point, so we make x2 is equal to 0. 64 divided by 8 is 8. x1 is equal to 8. So 8, 0 is our first point. We repeat that. We make x1 equal to 0. We divide 64 divided by 4. x2 is equal to 16. So 0, 16 as our second point. And we see that here. 4, 0, 4. Right here. 16, 0, 16. And down here, 8, 0. This is our first line that represents everywhere where labor is used at complete capacity. We go back, we do the same thing here. We make x2 equal to 0. x1 is 48 divided by 2. x1 is 24. We make x1 equal to 0. x2 is 48 divided by 12. x2 is 4. That's supplies. So we see that line right here. Here's our first point. Here's our second. We connect. Here we have enough labor but not enough supplies. Here we have enough supplies but not enough labor. Here we have not, it's a maximization. So here we don't have enough labor or enough supplies. Only in this situation, these production choices here, do we have enough labor and enough supplies. So our possible choices are right here. 0x1, 4x2, unknown because we have to solve algebraically, and 8x1, 0x2. These are our three possible correct choices. This is how we solve graphing problems. Hopefully everybody's clear. You have the videos to watch. If you are unclear, you also have me to contact if you are unclear. This is what we are going to do now is I'm going to put each of the problems on the board for 7 minutes. Problem number 1 for 7 minutes. You have 7 minutes to solve and or copy the information to solve on your own. Problem number 2 will be for 7 minutes, and problem number 3 will be for 7 minutes. So right now, let's begin with problem number 1. If you have any questions, please contact me through Kakao. 7 minutes from now, I will change to problem number 2. All right, here is question number 2. Finally, the last question. All right, everyone, that's it for today. Thank you, everybody. Please remember you don't have to submit these questions, but answering them will be important for the attendance quiz. Thank you again for listening. I'll see you in our next class.